Hey everybody, we're going to do a lesson today on what's called inductive reasoning and counterexamples. As usual, you should probably not copy down literally word for word everything that I write, nor should you only copy down things that I write. You should be listening to what I say and making additional notes as needed. Most of what I have written today are examples. You probably don't need every single example that I have because that's not enough information. And you probably also want to make some extra notes about why these examples are what they are. So, enough said. We're going to be doing 2 days on 2 different types of reasoning, 2 different ways of coming to conclusions. The first one is called inductive reasoning, and then tomorrow I'll post a video about deductive reasoning. Inductive reasoning is just a way to come to a conclusion. So actually, I can write that, a method of drawing conclusions. But it comes from by observing patterns in the data. Now, when you hear the word pattern, you might think of patterns like I have in the gigantic word patterns here. It goes blue, red, green, blue, red, green, blue, red. Probably green would come next if there was another letter there. Or you can think of the patterns of the red stripes or the whatever. And those are patterns. Patterns are also just simply any observable reoccurrence that lets you come to a conclusion. So, for example, throughout your entire life, after all of the dogs you've seen in your entire life, you've noticed that they all have whiskers. So you probably come to the conclusion that probably all dogs have whiskers. Maybe you didn't come to this conclusion. We're not necessarily sure if it's true, but we're making that conjecture, we're making that guess that probably, after all the dogs I've seen, every dog I've seen so far has had whiskers, so probably we can make a rule all dogs have whiskers. To make it a little bit more mathy, after seeing the list of prime numbers 2, 3, 5, 7, 11, 13, etc., 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 maybe you come to the conclusion that all prime numbers that are greater than 2, so all of these, are odd. Maybe you're like, well, 3 is odd, 5 is odd, 13 is odd, 19 is odd, 23 is odd. Okay, probably, maybe they're all odd. Maybe not, but maybe they're all odd. And I just want to give you a warning that this way of coming to conclusions, it's helpful, it's useful, it's what our brains do all the time to come up with basic rules to explain the world around us. But it's definitely not a way to prove anything. It is just simply, it helps you suggest rules that may be true. So maybe you come across a dog someday that doesn't have whiskers, and suddenly you know that this is no longer a true statement. But until that day, nothing is going to suggest that you've come to the wrong conclusion, but you just haven't proved it. Same thing here with the odd and even prime numbers. Maybe there's a way to prove that there's no even number that's prime aside from 2. Maybe there's a way to prove it. Maybe you know a way to prove it. But for now, this is just a guess based on the patterns that we saw in the data. So that brings us to our other word for today, which is counterexample. And so if somebody has suggested a rule, for example, somebody has suggested this rule right here that says all dogs have whiskers, and you don't think that that's true, what are you going to do? How are you going to disprove them? Well, you're going to use what's called a counterexample. So in this case, so the definition is an example that disproves the conclusion of an if-then statement, but satisfies I should have said satisfies the hypothesis. So I can't spell. Hypothesis. Okay. So why do I say that? Why do I say it disproves the conclusion but satisfies the hypothesis? Well, up here, the hypothesis is dogs. We're saying if we see a dog, then it will have whiskers. It will have whiskers. That's kind of a way to rewrite this. And it has, so a counterexample has to satisfy the hypothesis. The hypothesis is we see a dog, or there is a dog, maybe would be a better way to say it, if there is a dog. So it satisfies the hypothesis. We saw a dog, but maybe it did not have whiskers. And so we're like, this rule is not actually true anymore because look, I proved it, or I disproved it. I found a dog, my friend's dog, and it doesn't have any whiskers. And so that's what a counterexample is. It meets the conditions of the hypothesis, but it fails the conclusion. It doesn't actually end up, the conclusion part doesn't end up being true. So let's see another example. It's a little bit more mathy. I liked this one because it has a pattern to it that I liked. It says all powers of 11 are palindromes. So as a quick review, power of 11 mean 11 to the first power, 11 to the second power. So anything to the first power is itself. So 11 to the first power is 11. 11 squared is 121. I know the first three. I don't know them after that. 11 cubed is 1331. Let's see. What is 11 to the fourth power? 11 to the fourth power is 14641. And okay, so then there's this other word that's kind of staring us in the face here. It's palindromes. Palindromes is just a fancy word that says if you read it forwards, it's the same as if you read it backwards. So for example, 1-1 is the same thing as 1-1. If you read it in the other direction, it's the same. 1-2-1, if you read it the other direction, 1-2-1. We'll jump down to the last one. 1-4-6-4-1. And we go the other way, 1-4-1-4-6-4-1. You read it backwards, and you still end up with the same number. So maybe, I wonder if maybe all powers of 11 are palindromes. So then we try the next one, and we say 11 to the fifth power, and I'm going to do it on my calculator. I get, 161051. And if I check it, I read it forwards, 161051. I read it backwards, 150161. That's not the same. So this is our counterexample. This is our way of disproving. It's hard to write and talk at the same time. This is our way of disproving this is a false statement. And I just want to highlight one thing. It does satisfy the hypothesis. It is still a power of 11. It is a power of 11, but it failed the conclusion. It is not a palindrome. You can't read it the same forwards as backwards. All right, that's all I got. Looking forward to seeing y'all in class.